Welcome back. In my last video, we did some performance benchmarking of LLMs running on different hardware, and it was really cool. I learned a few things from that. Shortly after that, my wife and I were driving back from Salt Lake to our town about an hour south of Salt Lake, and we got passed by 3 Lamborghinis on the highway, not going particularly fast in the same traffic we were in. And I remember thinking, those are so much faster, but we've got them artificially constrained. We don't really get to see what they can do when they're in this environment. And those same thoughts hit me about my performance testing in the last video. We made all the machines run Ollama. We made all the machines run the same model. It's no wonder that some performed better than others. Some are more optimized for that experience. Like our minivan was just as optimized for rush hour traffic going from Salt Lake to Provo as those 3 Lamborghinis that passed us. So it made me wonder what would happen if we really opened these up and gave them the engines that they wanted, gave them the models they wanted, and then threw the same inferencing tests at them. And so I've spent a month working on it, and I'm sad to announce that 2 of the machines, half the machines actually got worse, maybe even 50% worse when I performance optimized them. So let's talk about what I've spent the last month working on and what it really means, because I think it's really important. Let's dive in. Okay, let's jump back into our tool. It's a little different now, but we're going to go ahead and we are going to switch, make sure we're on Ollama. This is the backend we used last time. And load our models. Okay. So this is these are the tests we ran last time. We expect the same thing to happen. This is a Llama 3.1, 8 billion parameters, and it's using a Quant 4. So it should run really quick. First thing it's going to do, it has to load the model. We see the max, just like we saw last time. Max are really quick loading this. A couple of these machines, especially the T2 and the Area 51, have to load from hard drive into system memory and then system memory into GPU. And so you can see it kind of sits for a little while. You can see the memory and the CPU go up. So we talked about all that last time. That was our first run. We're going to run it again now that the models are warm, and we see that things run much faster here because we've got everything loaded, everything ready to go. So this is what we saw last time. I think this is a little smaller model, so it runs a little faster, but our T2 workstation is running 169 tokens per second. Our Alienware Area 51 with the RTX 5090 is running 162 tokens a second, and the MacBook Pro is coming in at about 60 tokens a second with our Dell Pro Max. This is the NVIDIA super chip. This is the desktop supercomputer. Is the slowest of those at 33 tokens a second. So 170, 60, 33. That's interesting scaling. This is where I've built this custom backend. So we're going to go ahead and for the T2 and the MacBook, we're going to run different backends. The NVIDIA chips, all of these are Blackwell, so they can run TensorRT-LLM, which is built by NVIDIA. It's specifically made for these chipsets. So we're going to run that. And then on the Macs, we're going to run, let me get this loading while I talk. This takes a little while to switch these backends. So on the Dell RTX, or the Dell T2 with the RTX Pro 6000, we're going to run TensorRT-LLM. We're going to run the same TensorRT-LLM on the Dell Pro Max with GB10. Both of those support it, and that is, we run it, we downloaded the Docker container straight from NVIDIA, and we're going to run it the way NVIDIA means it to be run. So both of those are running like that. And then on the MacBook and the Mac Mini, we're going to use Apple's MLX, which takes advantage of the Metal backend. Because we don't have CUDA cores on these machines, that's really optimized for their hardware architecture. And so we're going to do that. And then on each of these machines, we run an optimized model for it. So we're going to be running we're going to stick with Llama 3.1, and we're going to run the 8 billion parameters. So we're in that same model, the same parameter class. On the NVIDIA machines, we're going to run an NVFP4. So that's the NVIDIA 4-bit floating point, which is a high precision floating point 4-bit model. And then on the 2 Macs, we're going to run a similar Llama 3.1, 8 billion, and we're going to run the MLX optimized 4-bit model. So let's take a look at this. You can see here's our model right here. We're going to hit select model just so it loads it. So here you can see color coded. We're going to really focus on these three. The other two, the Alienware and the Mac Mini, aren't nearly as important for this test. It's really these three are the big differences. We're going to run the same test. The first run is going to take a while because TensorRT-LLM is slow. It is slow to load. I'm sorry, it's not slow. It's fast. It's slow to load models. And it's really built to be optimized. You run it and then you let it run. You don't keep loading and unloading. So the MacBook's already done. The T2 and the Pro Max, TensorRT is still loading the model. And so it takes it a minute. We're going to let it go. And it'll keep loading. Give it just another minute and we'll see it come in. All right, so the RTX Pro 6000 is done really quick. And the Pro Max is finishing up here. While that's finishing, let's look at this. So we just had 170 tokens per second on Llama 3.1, 8 billion, 4-bit model on Ollama. If we look at what TensorRT did, it's about 81 tokens per second. That's like less than half the speed. This is the optimized backend with the optimized model, and we're running at half the speed. Likewise, with the Pro Max GB10, we were around 40 tokens a second, and now we're sitting at 19.2 tokens per second. Again, Llama 3.1, 8 billion. This is the custom NVFP4, also a 4-bit model. This is optimized for this architecture, and it's half the speed. On the other hand, with the MacBook, we were running same model, 8 billion parameters, 4-bit on Ollama, and it was running at 60 tokens a second, and it went up to 100 tokens per second. So optimizing this use case, we cut two of our high-performance machines. The performance got cut in half, and our MacBook, the all-purpose, all-around machine, actually increased by, what is that, 50% better? This was pretty troubling to me. And so this is what took me a month to figure out. Let's talk about this. And I'm going to have to break off of our benchmark tool here because so much of what I did was in a lot of custom scripts and Python scripts, which I won't make you watch them. It gets really nerdy there. But let's talk about what happened and why. Let's dive into that. Okay, here we have some graphs and some data points. This is actually done in ChatGPT. It helped me visualize all this data. Let's start by looking at the startup time of these models. You'll notice we sat for a long time waiting for TensorRT to load, and then it was really slow. And then it took a long time to get that first inferencing test out. So this is with the custom backends. So the RTX 6000 and the GB10 are both running TensorRT, and here in the middle, the purple one, is my MacBook with the Mac M4 Max processor in it. So this one's the middle one, the Mac, is running MLX. The two on the sides are running TensorRT. When we loaded the 8 billion parameter model, it took 34 seconds for the RTX 6000 to load TensorRT and get that model ready. In comparison, it only took 12.89 seconds for the MacBook to load MLX with its model. And that desktop supercomputer took a whopping 75.75 seconds to load the 8-bit model. That's incredibly slow to load the model. It gets even worse if we switch to the 70 billion parameter. Here we jump up to over a minute for the RTX 6000. The M4 Max stayed right around the same amount of time, and that GB10 went from 70 seconds to a minute and a half, over a minute and a half to load the 70 billion parameter model. So this is slow startup times. Again, this isn't looking great for the RTX 6000 or the GB10. Let's look at our next test that I did here. And I ran each one of these multiple times. And so I know this data, well, it's averaged across a couple different runs. It's valid data. And we'll talk about the why here in just a minute. So let's compare the two tests I just showed you in my benchmark tool with what we're seeing here. When I run them just straight command line, and this isn't going through my benchmark tool at all, so it bypasses my wrapper scripts and those things, and I am just going straight to the engines and calling them over APIs. So this is true and repeatable. When I run that first model we did, the Llama 3.1 8 billion 4-bit, running the same one across all of them. So this left column here, 180, 60, and 30, that's pretty consistent with what we saw. I think it was 170, 60, and 40, if I remember right. Very consistent here. We're within 10 tokens per second. This is how fast it's generating those tokens when it runs. In Ollama, we see those repeatable data right here. When we use the optimized model, it cut by more than 50% on the RTX 6000 cut by about, well, not quite 50% on the GB10, and then it increased by 50% on MLX. So right off the bat, that tells us Apple is really good at optimizing their back end when you use their models running on their hardware. That's awesome. So definitely saw the performance bump there, but why did things fall apart with TensorRT on both of these? And so big question there. In the comments on my last video, I forget who it was. I'll have to go look it up. But someone asked the question, you got to look at batching and concurrency. And so I went ahead and I dove into that. And let's talk about that for just a minute, what batching and concurrency means. So concurrency is how many queries can I make against it? How many tasks can I give it to do simultaneously? So we're running our model. We hit it with an API call, and then we hit it with another API call at the same time and ask it to do something unrelated. Or, I mean, it's the same thing. It's still inferencing, but we give it 2 simultaneous commands, or 4, or 8, or however many. This is what TensorRT is built to do. And honestly, this is what this hardware is built to do. If we look at the graphs for this, so, well, let me paint another, let me extend my earlier metaphor. When we were in our minivan driving down the freeway, we got passed by 3 Lamborghinis. Each of those Lamborghinis had 1 person in it. Our minivan had 6 people in it. That's an example of batching. When we send 1 minivan down the freeway, it has 6 people in it. Each of those Lamborghinis only had a single. Then concurrency would be when we send that Lamborghini from Salt Lake down south, we send 1 at a time, and we have to wait till it gets there to send the next one. That would be no concurrency, single operation at a time, serial operations. Concurrency of 2 would mean, well, that one's driving, we allow a second car to go. And so allowing 2 minivans to go down the highway at the same time. So when we start adding batching and concurrency, we can generate an awful lot more tokens. What this starts to show, if we go back to our earlier graph, and this is my hypothesis, this is not proven, but I believe this is true. If you look at the difference between these, 180 tokens per second, 60 tokens per second, 30 tokens per second. If you look at the memory speed of each of these machines, the Dell GB10 is about 275 gigabits per second is the memory speed on that. The MacBook M4 Max is almost double it. It's I want to say it's like 550 gigabits per second, if I'm remembering right off the top of my head. So if we double our memory speed, and then when we go to the RTX Pro 6000 is like 1.7 terabits. We see that scaling right here, which makes sense because inferencing is very RAM intensive. RAM becomes your bottleneck because as we write one token, we have to be aware of previous tokens so that we have coherent sentences. We're not just generating random tokens. And if you remember in my previous video, image generation on the GB10 was surprisingly fast. It was much closer to the 6000 and blew the Mac Pro blew it out of the water. But image generation is very compute intensive. Once you get the data in there and let those cores loose on it, they're not starved for data. But all these operations, inferencing and training, are very RAM intensive. And so I'm betting what we're seeing there, it seems correlated to the memory speeds. And then, so when we jump back down to what we were talking about with concurrency and batching, if we batch things, we send all this data in, and we actually allow it to use more compute simultaneously. So look at this. This is where it gets really interesting. MLX crashes if you try and send it multiple concurrent requests. It's written on Python scripts. You will seg fault. You will crash your Python script. The only way you can do this is you actually have to spawn a second instance, load the model a second time, and then you could do some concurrency. But it's not true concurrency because I can't use all the RAM. I'm now only cutting it in half or in thirds. So no concurrency with MLX. It is optimized for single user serial operations. But let's look at what happens with the RTX 6000 and the GB10. So actually, let's take the GB10. Again, this is the 8 billion parameter model. And you can start to see, if we run a single operation at a time, we were at about 21 tokens per second. If we run 2 operations at the same time on that 8 billion parameter model, we see significant increases in performance. 2 operations, we jump clear up to 88 tokens per second. So running 2 at the same time gets us way better performance. And we see that scales almost linearly clear up to running 16 operations at the same time. And if we're doing that, we're generating 633 tokens per second on that same thing running TensorRT. So 21 tokens per second is not impressive. But if we're running this as a desktop supercomputer, we probably aren't limiting it to a single person at a single time running a single query. We want it to be available so that multiple people can hit it at the same time, multiple people can run against it. So that supports it. That is where this GB10 shines. It's not using it as a single machine that I run Ollama and I ask it a query, let it churn, it spits it back. I ask it another query, it churns and spits it back. I get way better performance running my Mac like that. If I'm running a server though, and I'm constantly bombarding it with multiple requests at the same time, I see a lot of performance increase on the GB10. Keep in mind the GB10 is a $3,000 machine. The RTX 6000 is an $8,000 graphics card wrapped in an even more expensive machine. I think these are going for like $12,000 right now. So this machine costs about 4 times what the GB10 costs. This one's really interesting. We saw it when we did a single batch. When we ran it one at a time, it was 88 tokens per second on the 8 billion parameter model. When we go to 2, it almost doubles. We see more than a doubling with the GB10, but this one almost doubles. And it only goes up a little bit when we go to 4. But then when we go to 8, and I spent almost a whole day diving into this, this is where batching starts to happen. When I send it 8 simultaneous requests, it packages all those like packing 8 passengers in a single minivan and then sends all that through in a single request. And we see an exponential jump right here when we go from 4 to 8 concurrent sessions because we take advantage of batching. And then if we run 16 simultaneously, this is like fully packing 2 minivans, sending them down the freeway at the same time. So I've got 16 people traveling in the amount of time. Even though it's a little slower, I can move 16 people from Salt Lake down south where that Lamborghini is only taking 1 at a time. So the Lamborghini is generating 96, or here our MacBook Pro is generating 96 tokens per second. But if we fully optimize and run that RTX 6000 concurrent and batching, we can get 2,600 tokens per second, 26 times what that Mac is doing. That's pretty impressive. So I wanted to share these. That's what I've been able to come up with. I hope this is helpful. What are some other interesting things we ought to look at? Drop me some comments. Let me know what you think. I guess the key takeaway for me right here is with AI in particular, you have to match the workloads to the hardware. It is not a one size fits all. If you're running a server, if we were building our little LLM that's running an API server and we want people to hit it, MLX is not that's not the platform you want to use because you've got to lock it. Single request, wait till it's done, next request. It might be really quick at doing those 1 at a time, but you're doing them serially and you're doing single token at a time. If you're looking at running something that runs multiple requests where you can have multiple people chatting with it, calling an API endpoint and doing inferencing like that, that GB10 is pretty cost effective for that. And if you're doing image generation, we saw that the GB10 is very cost effective for that. That's a great platform for this. The RTX 6000 If you don't mind paying, I think it's like 5 times the power budget. If you want 5 times bigger electrical bill and you have 4 times as much to spend on the machine, you get amazing performance out of that. But matching the workload of what you're doing to the hardware, to the engine, to the model, it really takes some understanding to really get this to work right. So I think that's the key takeaway for today. Drop me a comment below. Let me know what you think. Is this helpful? Do you have any questions? Look forward to your questions. Look forward to your comments. Please let me know what I can do for you. Thank you. Take care.